Okay, so welcome to the next lecture. I left you last time, we were talking about supernovae remnants and asked you to evaluate how far a supernova remnant will travel across space in the sort of period of about 1 million years, which is how long it takes before they expand so far that they get stopped and come into sort of some kind of pressure equilibrium with the interstellar medium. And I suggested use an average speed of 100 kilometers per second, which you can see here. So obviously the distance is just velocity times time. You've done this a few times now, but it's always good to put the numbers in for yourself. So here you go with 100 kilometers per second for 1 million years, and here's seconds in a year again. So that gives 3 × 10⁻¹8 meters, or about 100 parsecs. Okay. So recall that the typical distance between neighboring stars is about 1 parsec. So this is, 100 times further than that. And again, in terms of volume, this is a volume of space that is 1 million times bigger than the sort of the volume between us and the next star. So you can see that it's these hot bubbles of gas are going to take up a large volume of space, especially when you've got them going off, every 30 years or so in our galaxy. And just by way of illustration, then here is a beautiful supernova remnant. So again, it's not a complete bubble by this stage because the interstellar medium is a very clumpy and inhomogeneous place. But you get the idea that an explosion went off here somewhere, and the hot edge of the hot bubble is now out here somewhere. So you can see it's traveled significant distance, so that's the edge of the remnant at that time. So actually this picture does quite a nice job at segueing into the topic we're going to look at today, which is interstellar dust clouds. I don't know if you can see, but on the right-hand side of the image here, in this region, there seems to be something sort of dark lurking here, which is not affecting the rest of it. And that coincides with the bright sort of sharp edge of this supernova remnant here. And that's because there's actually quite a slightly more denser cloud of interstellar gas and these interstellar dust particles here, and that's slowing down the supernova remnant in this direction and giving it that sharp edge. And it's these dark clouds of interstellar dust that we're going to talk about today. So we're going to talk about 3 different effects of interstellar dust. Its extinction effect, which is the idea that it causes objects to be dimmer than they really are. Its reddening effect, where it causes objects to appear redder than they really are. And then we'll look at, those are sort of, to do with dust absorbing and scattering radiation. And then at the end, we'll look at how dust emits radiation. And that will bring us very much to the infrared window of observational astronomy. So let's deal with the kind of dimming or extinction effect of interstellar dust first. So you've basically seen several examples of this already. I've shown you pictures of galaxies where there are these sort of what appear to be dark lanes running, especially along spiral arms in galaxies. We've seen examples of them in galactic nebulae as well. So that sort of dimming effect where you see a dark lane is definitely the most obvious manifestation of interstellar dust when you're looking at optical pictures. So basically what's happening is that the cloud of dust and gas, but it's the dust that's doing the absorbing here, is blocking the background starlight or nebula light. Okay, so again, you need that particular geometry. You need a source of background light, whether it's a load of stars or a nebula like an H2 region. Then you need a cloud of dust, and then we are the observer over here. So what is this dust? Well, they're basically small solid particles. So it's not like an atom or an ion or a molecule. These are actually solid particles. Okay, they're quite small, as we shall see. Less than a micron in size, and they are sort of uniformly mixed in with the interstellar gas. They move around together with the gas that we've been talking about. And basically, wherever there is interstellar gas, you will find dust to go with it. Okay. If you're wondering what they're made of, then basically they come in sort of two types. Again, this is not part of the module, but just in case you're interested. So you either have sort of carbon-rich particles, a bit like soot, okay, or more silicate particles, which are basically like literally like grains of sand, so basically a mineral composition. And again, if you're interested in where they're coming from, they actually come from they're made in this sort of cool atmospheres of red giant stars, which are, you know, they're down at 3,000 Kelvin. They lose mass from their dense atmospheres, especially as they get towards the planetary nebula stage. And basically solid particles condense out of those cool, dense atmospheres and then get ejected into space, which is why they end up in interstellar clouds. So just to flesh out that bit about the size, there's a whole range of sizes. They are a bit like, literally like grains of sand on a beach. So you've got lots and lots of small particles, and they can be really small, like down at 5 nanometers. So, you know, they're not much, they're just a bit larger than sort of some of the large molecules that you find in interstellar gas, the cold gas. And they go up to about 0.5 micron in size, so 500 nanometers. And in terms of optical pictures, then this is important. So the fact that the grain size is similar to the wavelength of light means that these solid particles are extremely efficient at interacting with light, with optical radiation. So the wavelength of the photon is similar to the size of the grain. These grains are basically dielectric materials. They interact with electromagnetic radiation very efficiently. And so again, this principle that it's a bit like a radio transmitter aerial. If you want to transmit a certain wavelength of radio waves, you will make your aerial the same length as the wavelength that you're trying to transmit or absorb. And it's a similar principle here. You sort of these grain sizes, if they're similar to the wavelength of the electromagnetic radiation, they will interact strongly. So let's have a look at a few pictures again. So here's, in the context of galaxies, so here's a galaxy that's beginning to tilt around to being close to edge on, and you need that geometry for the clouds on this near side of the galaxy, the side that's closer towards us, to block the light from that's generated on the far side of the galaxy. So all of this stuff here is, all that dark patches, dark lanes are all due to the extinction effects of dust. So extinction is a term that is a combination of both scattering effects and absorption effects. So scattering, where a photon is redirected by the particle, and absorption, where the photon is destroyed by the particle and absorbed. So here's another famous galaxy, referred to as the sombrero, perhaps for obvious reasons. It's actually one of these lenticular galaxies. So you've got the old stellar population here, but there's clearly a dusty disk in here as well, and you can see that blocking the background light from the rest of the galaxy there. And if we go to another lenticular that is almost precisely edge on, you can see the dust in the disk component here, beautifully silhouetted against the background starlight. So that is what dust extinction does in the context of galaxies. But we have a lot of dust in our own Milky Way, and so we need a way to deal with it, because it has obviously significant effects on objects that we observe. So this effect of extinction is the idea that an object will become dimmer, or will appear to be dimmer, because there is dust along the line of sight between the object that it's emitting and us observing. You've got dust along the line of sight, and that will make the object appear dimmer than it really is. So this amount of dimming due to the dust, because brightnesses of stars are measured in magnitudes, then the dimming effect of dust is also measured in magnitudes. So we need to reuse the magnitude system again here. And the total, the amount of dimming is referred to as the total extinction. Okay? And if it's measured in the V band, as we talked about earlier in the module, then that will be the total visual extinction. And so total visual extinction is given the symbol AV, okay? And it's defined in a sense, so mathematically putting into words what, putting into maths what the word said here. So the amount of extinction along a line of sight to a star is the difference between its observed apparent magnitude. So little mv is the apparent magnitude. So this is the magnitude we would actually observe. And this, what I'm going to call the intrinsic apparent magnitude, is the apparent magnitude the star would have had if there was no dust between us and the star. Okay, so this is the, in a sense, the true apparent magnitude that the star should have if we had a clear view of it, but this is the actual apparent magnitude we observe here. And of course, this will always be a positive quantity because the dust is going to make the object appear fainter. And remember that if the object is fainter, then its magnitude number will go up. Okay, so the observed apparent magnitude will be greater than the intrinsic, and therefore this is a positive quantity. Now, sort of where this starts to, clearly become important. Hopefully you can illustrate this to yourself in a moment. If we actually now need to adjust, because of this formula, we need to adjust the formula we met earlier, which relates apparent magnitude to absolute magnitude and includes the distance. Okay, so previously we didn't have this AV term here on the end, but of course the absolute magnitude is a property that's intrinsic to the star itself. And when we had the equation before, then we were assuming that the apparent magnitude was also the intrinsic apparent magnitude here. But now we see that the observed, if this is the observed apparent magnitude now, then we have to account for this effect here of the dust. Okay, so why don't you have a little go at seeing the effect that not taking, if you ignore the effect of dust, you can get into real trouble and you can derive completely the wrong properties for the object you're looking at. So to try and illustrate that to yourself, have a go at this little problem. So by what factor would you get the distance wrong? So I'm only after a factor here, okay? So how many times, further away is the star than you think it is? If the star had a total visual extinction of 1 magnitude and you ignored the fact that it was there, okay? So if the star had this visual extinction AV of 1 magnitude, but you worked out its distance ignoring that effect, compare the two, what's the difference? Okay. So remember, use the magnitude system. So you've got a difference of 1 magnitude. So in a sense, what factor does that correspond to in terms of distance here? Okay. Okay, so have a little go at that, and we'll come back after the break to have a look at the reddening effect.